Hi, everyone. Thanks for joining us today for this webinar covering metric management on SigOpt. Um, we waited a couple minutes, so I think it makes sense to get this kicked off just so that we stay on schedule. So I'm really excited today to present SigOpt's first complete solution, which is metric management. I'm Barrett Williams, Product Marketing Lead, and today we're joined by Harvey Chang, SigOpt Research Engineer, to present a live demo of many of the features covered in this solution. Just to give you all a little bit of background, in case you're new to Cecrops, our mission is to accelerate and amplify the impact of modelers everywhere. And that means that we've built a platform that makes optimization scalable, easy, reliable. Every model can and should perform better with optimization. If you're already a user, you may be familiar with where we fit in the modeling stack. But as you can see, we sit at the center to facilitate insights, model tracking, collaboration. This generally happens after the data preparation step, and we integrate with your existing infrastructure. So with Python-based libraries, client libraries, as well as Java, our customers typically use us in notebooks or from Python scripts. But really, we're a REST API, so we can effectively be called from Keras, from MXNet, from really the modeling platform of your choice. And that means you also get to use your own infrastructure, whether that's on-premise, whether it's hybrid, multi-cloud, or one of the public clouds. We have customers using all of these implementations, especially in the financial services and defense space. On-premise seems to be the way to go for younger and more agile companies. Multi-cloud is how a lot of our customers deploy their model training infrastructure, and also how they call the SigOpt API. This is our interaction diagram. So as you can see, when you're training your models, your training data, your testing data stays private. In today's example, Harvey will be using Google Colab and Google Drive to store the training and testing data. And he'll be using the SigOpt API to send hyperparameters, and we'll be receiving new configurations to iterate through the training loop. This ends up producing better results. And you can also track various metrics. You can even tune against multiple metrics, which I'll get into in a moment. And this goes back to the fact that SigOpt integrates with any modeling stack. So you can use your existing stack and still get experiment insights, still use the optimization engine, and also take advantage of the fact that SigOpt is a robust enterprise solution, handles scale on a number of dimensions. To give a little bit of background, metric management is the last in a long series of developments that we've incorporated into our product. So in the early days, we began by providing an ensemble of global and Bayesian optimization. And what was unique about that at the time, and still to some extent, is that we can handle a wide variety of parameter types. We then scaled up our solution to accommodate a lot of our more demanding customers' needs by providing millisecond latency and also parallelization. So if you have a large GPU cluster, we can provide asynchronous suggestions to all of your running instances. With advanced model optimization, we added a number of features that our customers were requesting, including early stopping for long-running and deep learning models, multitask or multi-fidelity, also for long training models. We can provide multiple solutions, and we also provide conditionals, which can be useful for different types of architecture search, constraints, failure regions, and we scaled up to facilitate over 10,000 observations. We support over 100x parallel and 100 parameters. We then added to our dashboard. So this includes experiment history. You can see your best result thus far. You can do things like examine parallel coordinates and see which successful parameters correspond to other successful parameters, as well as get insights out of multitask optimization. So again, that multi-fidelity approach. So what's new today, and we've been working on a lot of these features over the course of a couple of years, but they all sort of come together, and they're really more powerful together than they are independently. But today we really encourage all of our customers and users to track any possible metric they can, because we support up to 50 metrics. We have a tool accessible through our API called Metric Strategy, which lets you select which metrics you're going to optimize, either one or two, and also select which metrics to store and which you'll be constraining. And so this all kind of nicely comes together to facilitate optimization for your business metric or multiple metrics. And you can switch out metrics over time as well if your business needs change. So for a lot of businesses and a lot of our customers, it's sort of tough to define and select the right metric. So a lot of models have accuracy or F1 scores, or you might want to minimize loss. But there might be an external business constraint, like governmental regulations, or maybe there's an engineering constraint on your model, like it can't be too big, or there's a latency requirement on your model. So really business contexts create the need for more than one metric, or they demand that you sort of change your metrics over time. So sticking to a single metric can be limiting or inadequate, and a lot of our customers call this a single metric trap. Sometimes people are just looking at the wrong metric. So to address this, there are really three things you can do. The first is to track and monitor so that you gather additional information as you're training, so you're aware of what's going on in your model. And that's really where metric strategy comes in. That's where you can choose what to record and what to optimize and what to set constraints around. Secondarily, you want to understand the trade-offs between your metrics. And that's where multi-metric optimization can generate a Pareto frontier, which lets you as the user and the data scientist determine which of your two metrics you're going to prioritize and by what amount, or whether you're going to prioritize them equally. And lastly, a lot of businesses have guardrails they need to apply to metrics. So in the example that we're going to be covering here, this is model size, but it could be things like memory usage or inference time. For autonomous vehicles, there's usually an upper bound of about 20 milliseconds for inference time per frame. And so in order to address these guardrail metrics, you can use tools like metric constraints, which will let you basically tell SigOpt to provide suggestions that basically meet unoptimized metrics as thresholds. So here's the full set of metric management features, and Harvey's going to present these in the demo. But metric storage is really the essential first step. You can track up to 50 metrics, which is definitely helpful if you want to look back and analyze or optimize different metrics later on. Metric thresholds helps you focus on optimizations that meet your business needs. So in this scenario, you may say your accuracy has to be above 97%, and otherwise, you can't ship your product. So that will induce SigOpt to only return results above that threshold, assuming that that's possible given your model. For metric constraints, this basically, you can apply any function to maximize or minimize above or below, and you can even adjust the constraint as your experiment progresses. And note that this constraint is on untracked metrics, so unoptimized metrics. And then metric strategy, as I mentioned, is SigOpt's API. So it really helps you choose and adjust and change which metrics you're tracking and storing versus optimizing versus constraining. And lastly, multi-metric optimization helps you optimize against two metrics at the same time. And one final feature that we've incorporated with customer feedback is in some cases, certain parameter sets will cause a training run to fail, or your model won't converge if you have, for example, too high of a batch size or learning rate. So we let you mark failed observation states as kind of a final way to induce SigOpt to avoid certain regions of the exploration space. So to get to our live example, we're going to be doing a road sign classification task. So this is a pretty simple image classification task. We'll be using Keras as our framework, and this is a convolutional neural network. And the constraint that we'll be applying here is actually on model size. So at left, you can see that red line, and you can see the blue dots are suggestions that are below the red line and are valid because the model is sufficiently small. But we're still looking to optimize our validation accuracy, as you can see on the left. So, in the first 30 to 50 trials, we're about 98% validation accuracy. And we go up from there, peaking at around 100 trials. On the right, you can see what the data set looks like. And this is actually a data set that Harvey augmented to make sure that the number of samples in each class is a little bit closer so that it's a more balanced data set. With all that said, I'm going to hand it over to our research engineer, Harvey Cheng, to show us the demo.
Great, thank you, Barry. Let me share my screen here. Okay. Hopefully everyone can see what I have on my screen. Yeah, so just as Barry just explained to you, the goal of this demo is to train a convolutional neural network. We're optimizing for the top one accuracy, recognizing these traffic signs, and we're putting a constraint on the size of the network. So started off, we need to pip install SigOpt, doing our normal importing SigOpt, and we're using TensorFlow and Keras. The data set that we use is the German traffic sign data set. I have already pre-processed this data here. Here I'm loading the data. If you're interested in it, you can click this link to see the pre-processing pipeline. So for the purpose of this presentation, I will be skipping that for now. The data is already split into training, validation, and test. We're doing a little bit of normalization here. Sometimes the data is stored as unsigned integer. We're just normalize it to a floating point. We'll be using the GPU instance on the Colab. Just here, I'm trying to look at what the GPU I'm using here, further setting up some of the, so there are a total of 43 classes, so 43 different signs. Each sign, the image of each sign is 32 by 32 pixels with 3 channels. Here I'm setting up the batch size for training, which is 32 samples, and we're doing an epochs of 10. Okay. Here I'm making the training label into categorical variables using the built-in features. So the base model that we use is inspired from this paper called MicronNet, which is a very simple convolutional neural network. Here is how I define the network. Basically, we have 3 convolutional layers and 2 dense layers. In particular, we're interested in tuning the hyperparameter that's related to the architecture. So in this case, the kernel size for the convolutional layer, the number of filters per convolutional layer, and the number of hidden units inside of each fully connected layers. Because we are most interested in constraining on the size, so these hyperparameter will have an effect on the size of the network. Obviously, you can also tune the learning rate of your network at the same time, but for the purpose of this example, we just set those as fixed. And down here, I'm setting up the way to training the model. So as I said earlier, I'm fixing the SGD hyperparameters. And here are the batch size and the epochs that we're training with. A couple of things that we want to keep track of during training the model. One of the things, obviously, the validation accuracy. We're also kind of interested in the test accuracy. We're obviously not optimizing on the test accuracy. We're only keeping track of that metric for further analysis. Another thing I'm interested in is the training time of the network. I want to see how different size model train differently. So that's something that I can do by using this callback function that I created. Basically, just looks at how long it does to do the backprops. Here I am creating this function that reports all of these metrics to SigOpt. As you may notice, I have some of these if conditions here. One of the things that I want to point out is this if block here. So sometimes, as Barrett earlier pointed out, that the model might diverge. So in the case of that, I have set some minimal threshold of validation accuracy to indicate to myself that the model might have diverged. For these instances, I will mark the suggestion, or I will mark the observation as failed. And then I will log the metadata of the training time, the validation accuracy, and I will also log the loss metric of the model to see what actually happened. So I might come back later and either rerun the model or do a deeper dive on what's going on. Other than that, we're reporting the size of the network, which is in millions over here, which is in million parameters. Obviously, the validation accuracy, the test accuracy, and the training time. Okay, let me run this block. And here is how we set up this SigOpt experiment. So over here, we have listed out the hyperparameters we want to tune and the associated lower and upper bound of each hyperparameter. And then here is how I define the metrics using our newest metric strategy. So the main goal is to maximize, so optimize the validation accuracy of the network subject to a constraint on the size of the network. And for here, I set the threshold and constraint to be 0.25, that's 0.25 million parameters. And then you can see I'm also storing the test accuracy of the network, and I'm also storing the training time of the network. In the meantime, I also try to log some of the metadata, the training file that I'm using, the environment, some of the other constant that I've set. And I can run this block. Okay, so now I can start my connection to SigOpt and then create this experiment. And I can start our training loop. So now the network has started training using suggestions given by SigOpt. We can take a look at what it looks like on our website. So right now we don't have any observation reported, so obviously this is blank. If we go to our property page, you can see that all of our metrics are listed here. I have my threshold, my optimized metric down here, and I have all of my metadata stored here. Okay. Okay, so we're not going to wait for this to, train and finish. So earlier I have started on a same experiment that I ran for about 70 observations. We can see what it will look like on your summary page. So on your summary page, you will see, your best values and your experiment improvement graph, just as your normal SigOpt experiment. If we go to the history page, we can see a list of observation reported. We have our failed observation when so when the network is diverged. So we can see, our loss function did not decrease at all. Scrolling through more, we can see some of these labeled with the size label with the red color. So over here, that means the size of the network did not meet the threshold that we have set for our experiment. So for this one, it's 0.35 is higher than 0.25 that we set. We can also look at the analysis page. So we have, as you can see in the experiment history, we have marked the observation that do not meet the threshold with gray. One of the things I like to do is to also look at comparing the different metrics that have logged. So for now, I can try to look at how size correlates to validation accuracy. So you can see this is the threshold that we set on the size. So we can zoom in and see what's going on. So maybe now, like after I've inspected this and I've seen we have, quite a lot of observation that already satisfy my constraint of 0.25 million parameters. And I say to myself, okay, maybe we can actually even shrink the threshold to be even smaller on the size. So because the best one we have observed so far, it's way below this 0.25. So I can do that very simply in the property page. So I can go to edit. I can say something like edit the size to, let's say, 0.15, and then submit. So this will indicate to SigOpt that we have set a new threshold. So let's do something different now. If you go back to the analysis page, you can see the improvement graph has been updated to show that because the improvement is with respect to observation that satisfy the threshold. So this has been updated. If we look at this thing again, and you can see now some of those old observations are now marked as not satisfying the threshold. And we can also do this in the API very simply by just calling this function experiments.update with the setting a new threshold on the size. So now that I have shown how this metric constraint and metric failure works, you can also combine some of these features together. Like I can also do a multi-metric experiment with additional constraints. So in a separate experiment that I have created, I do not have the code for now. So in this experiment, what I'm trying to do is I am trying to optimize both the validation accuracy and the max. So the max is the multiplication, accumulation, computation. It's kind of like how many flops your network uses. So I'm trying to think about, in this sense, I'm trying to think about how the accuracy of the network corresponds to the complexity of the network. And at the same time, I also have the same constraint on the size. So as you can perhaps see in here, so have constraint on size and can do something like this. Oh, maybe it's easier in here. And one of the interesting things that we can see that maybe something like before, if we don't have the constraint on size, some of these observations we'll consider as Pareto optimal. But now that with this new constraint on size, they are no longer considered feasible for us, and we have different set of observations that are considered as Pareto optimal now. Okay, so I think that concludes my share. Sorry. That concludes my presentation here. I guess just want to quickly recap what I've done here. So with metric storage, we can track auxiliary metrics such as training time and test accuracy for later analysis. With multi-metric optimization, the goal is to optimize competing objectives and understand the trade-off between them. In this case, in the last example that I gave is the validation accuracy and the number of like MAC operations. With metric constraint, I can set a threshold on the size of network. So that indicates to SigOpt to only suggest network that, to give me more networks that satisfy this constraint. And with observation or metric failures, I can mark diverged network as failures to resolve for further investigation. Now I'm going to hand it back to you, Barrett.
Thanks, Harvey.
Do you want me to stop sharing?
Yes, please.
Okay.
Yeah, I think I got it. There we go. Yeah, so thank you so much, Harvey, for reviewing all of the wonderful features that comprise metric management. I just want to review a little bit of what some of our customers have done with the platform. So Peter Willender, a research scientist at OpenAI working on reinforcement learning, has found massive productivity improvements for his team. Metric management is just another way to kind of guide the experimentation process for data scientists at OpenAI. And similarly at 2 Sigma, one of our financial services customers in the algorithmic trading space, a lot of Matt Adaris data scientists have been able to achieve higher productivity with much more guided experimentation. You can read a blog post from Matt on the 2 Sigma website. I'm going to open up for questions now. If you'd like to submit in the Q&A window on chat, and I can also unmute all participants. You can feel free to unmute yourself if you have a question. Okay, I don't see any questions today. If you guys are looking for where to head next, feel free to check out our YouTube channel. I'll send out the slides after the webinar concludes, and so you can click on this link. We especially have a lot of content on algorithmic trading and multi-metric optimization. Harvey has been generous to publish the experiment, so you can actually click through using a guest API token. You can also head to sigopt.com/tryit to try out our solution and get an interactive demo that's tailored to your business's needs. And we have 2 more upcoming webinars. We just launched a new feature called Prior Beliefs, courtesy of Harvey and his team. So on Thursday, June 4th, we'll be covering warm start tuning with prior beliefs. So If you want to introduce prior information to your optimization run before kicking off your experiment, you can now do that. And then on Tuesday, June 9th, we'll be covering some research activity we did on detecting COVID-19 cases in X-ray images of lungs using deep learning. And we optimized a COVID-19 detector network. As always, you can find us on GitHub, LinkedIn, or Twitter. Feel free to star our repos or like any of our posts or follow us. And thank you so much for joining today. We really appreciate your attendance, and we look forward to working with you in the future. Thanks a lot.